Suppose we have a system of particles and we are looking from in G frame in ground frame. So we have some particles, say this is a M1 particle of mass M1, then particle of mass M2, and a general particle, say ith particle. So suppose its mass is Mi, and then the Mn. These masses are moving with velocities, say v1 vector. These are velocities in ground frame. V2 vector, something like this. This is a vi vector, and the nth particle may be moving with vn vector. And then center of mass may have some velocity. Suppose there is center of mass, and the system center of mass has a velocity, say vcm. So total kinetic energy in the G frame is nothing but a simple sum of like Ki. K is equal to the sum of all the individual kinetic energy. So I just want to write the kinetic of the Ki ith particle, and all these energy will be added from I is equal to 1 to n. And the kinetic energy of the ith particle can be simply half its mass mi and speed square, and that can be written as more elegantly like vi dot vi. So this is the total kinetic energy of system of particle in the ground frame, and this is what is in the bracket. This is in the bracket, this thing is the kinetic energy of the ith particle, and then I will have to add all such kinetic energies. And now I'll use a result of relative motion. What result? That the velocity of the ith particle can be written as a velocity of ith particle with respect to center mass plus velocity of center mass. This is a simple chain rule of relative motion. So vi dot vi will be simply vicm plus vcm, and its dot product with itself, that is a vicm plus vcm. So if I make a dot product, so I will get first term will be simply vicm square, and then vcm square, and then there will be two cross terms. So that will be how much? Twice of vicm dot vcm. And put this in the first expression, the expression of the total kinetic energy. Let's go in the next page here. So total kinetic energy that I written was summation of half mi vi dot vi. Or let me put the value of that vi dot vi. So this is summation of half mi vi dot vi. I had obtained vicm square plus vcm square plus twice vicm dot vcm. Some rearrangements. So some rearrangement will lead to that k is equal to summation of half mi vicm square. That is the first term. In the second term summation, like vcm is a constant for the whole system, so I can take that vcm square outside the summation. So for the second term, I am rearranging like summation of half. Even I can take half outside. So first, let me take half outside. Half summation of mi, and then vcm square. And the last term, again I'll take vcm outside the summation, and this 2.5 will cancel, so that will become summation of mi vicm, and vcm I have taken outside the summation like this. So now let's see what does each term mean. First of all, let's see this. This is mi vicm. What is mi vicm? Mi is the mass of ith particle. Vicm is the velocity of ith particle with respect to center mass. So MIVICM is the momentum of ith particle in the center mass frame. And this summation then becomes the total momentum of the system of particle in the ith in the center mass frame. And we know that in the C frame, total momentum is zero. So this term will become zero. So this term is zero. And what is this term? So this is nothing but the kinetic energy of the ith particle in the C frame. What is half mi vi cm square? Mi is the mass, vi cm is the speed with respect to center mass. So half mi vi cm square is the kinetic energy of the ith particle in the C frame. So its summation is the total kinetic energy of this in the C frame. So what I can write now? I can write like K is equal to K. This K is the kinetic in the ground frame, and this is the kinetic in the C frame. So that I'm writing KCM. And the simple thing, the summation of Mi is the total mass. So that will then become plus half into mvcm square. And this is the required expression that we wanted. So this is the total Ke in G frame, that is the ground frame. And this is total K in the C frame. And this is total mass, and this is the velocity of center mass. So this is the relationship between the kinetic energy of a system particle in the C frame and G frame. It's a very important relationship. And remember, we have not put any restriction. The system particle can be a rigid system particle and can be any fluid or can be some discrete particle system. And the same result will be used in the rigid body dynamics for a CTRM, because after all, this result is valid for any system of particle. So this is the expression.